There are a number of different experiments that are usually talked about in the context of demonstrating the effects of quantum mechanics. The one I want to focus on here, and the one that might make the most intuitive sense, and the one that shows some of the strangenesses of the ideas, is something called the photoelectric effect. Now, we already have some ideas already about light, and we have some ideas about the flow of electric charges. So one of the things that we now know about light, according to Maxwell's equations, is that light is supposed to be a wave, and light is supposed to carry energy. If we also have the view that if we treat the atom as basically you have some sort of proton, and then some sort of electron going about that proton, some sort of setup like this, we have the idea that if you were to come along and hit the electron with enough energy, such as from light, some sort of light wave, the energy might be enough so that way the electron and proton are no longer bound together and they fly off. It's kind of the same idea that if you were to imagine you have some sort of satellite going around in orbit, the Earth, and you really fire the rockets really hard with so much energy that it leaves orbit and it shoots off, never to return. So the idea then is, well, suppose I have a sheet of metal like so, and I start shining the light on it. One of the things that I can then possibly expect is electrons to then start being fired off. And so I'd get some flow of charge, and I can measure that amount of current flowing. I can measure the energy of those electrons, and then try to use something like that to then describe the atoms that they're being fired off of. And we use metals in part because there are these electrons that are easily to kick off. Metals will tend to have electric charges flow through fairly easily, so this is usually what the experiments are going to do. Now, if we're treating light as a wave, there are basically two properties that we can look at. One is the frequency of the light, or the angular frequency, and the other is the amplitude of the light itself. And the classical way of thinking about it is, well, with a bigger amplitude, we're basically talking about light waves with more energy, and the same way with sound. High amplitude sound means it's really loud. It's a whole lot of energy packed in. So our intuition then would say that, okay, if we use brighter light, we have higher amplitude light, and so it would have more energy. So again, we can have the same sort of thought. We'll have light coming in, and it'll be some sort of light wave coming into the metal, and it can start shooting off electrons. And the higher the amplitude, then the faster the electrons should be going when they're kicked out. They'll have more kinetic energy when they're hit. There is probably also some lower end of the amplitude of light where the electrons aren't shot out anymore. In the same sort of way, if we were imagining there's a satellite going around the Earth, if you don't give it a big enough kick, it won't leave Earth orbit. It might change the orbit a bit, but you're still stuck in there. So the same idea we could think of is like we need at least bright enough a light to have electrons get shot out. And the brighter the light, the more energy the electron should have. So we want to do the experiment, we test that, we look carefully, and the results are a bit interesting. So there are two different variables that we can adjust with the light, the amplitude and the frequency. Now, when the experiments were done, this is what was discovered. As the amplitude increased, the current got larger. So one of the interpretations would be, okay, well, then we have electrons firing out, and if there's, of course, the same number of electrons, the current's greater, then they must be moving faster, they have more energy. But carefully looking at it, we actually found that the potential energy that must have been shot out from it, if we basically look at, see, okay, what potential difference do I need to stop these things, we find that the amount of energy these guys had, the potential it took was the same. Didn't matter how bright a light I got, basically what it looked like is, well, while the current increased, the amount of energy per electron was the same. So I'm getting more electrons, but not more energetic electrons. With the greater frequency, we find that we can actually have the potential difference that we need to stop these things becomes larger. And there's also a certain frequency, some lower bound frequency, where the potential difference that those electrons have, what we need to stop, is basically going to zero. And if you are below that certain frequency, no matter how bright a light you use, nothing comes out. That's very strange then. It seems like, okay, well, if we're increasing the amplitude, there should be more energy. But we see if we don't use high enough a frequency of light, no matter how bright we get it to be, nothing comes out. We need at least some higher frequency than that. And if we make it brighter, the electrons don't have more energy, there's just more of them. So, what is the solution? The solution that Einstein came up with, and what he actually got the Nobel Prize for, is applying the quantum principle that instead of treating light as just a wave, we'll treat it as something that has a certain amount of energy packed in, a certain quantum of energy, a certain quantity. That's where quantum ultimately comes from for quantum mechanics. So we'll say that light of a certain frequency, it's going to have some amount of energy in a photon, what we used to call a particle of light, and the energy it has is going to be dependent on the frequency of that light and a constant that Max Planck came up with in his work, and so this is the Planck constant. The Planck constant has a value that, as measured, is 6.626 times 10 to the minus 34. And as you can guess, so we can have units of energy overall. When we multiply by frequency, it has units of joules times seconds, or joule seconds. So obviously you need a pretty high frequency if you want there to be a lot of energy. But the basic point then is we can apply this and then talk about the energy of any electrons that are being shot out. So the kinetic energy of any exiting electrons being fired out is going to equal the amount of energy shot in by a photon minus what we will call the work function. And basically this is like the minimum threshold you need to get out of the atom, to kick the electron out. So if you were imagining it's like some sort of well that you're inside, we put an electron down there, and since the well is so deep, that means you need at least so much energy to lift it up and get it out of there. And if you don't have enough energy, you don't get it out. But if you do get it out, then it'll have some amount of kinetic energy, and it'll depend on what's left over. Notice, of course, one thing, that if the energy in the photon is less than the work function, that would suggest that the kinetic energy is negative. Well, that makes no sense. There's no way we can have negative energy. So this is only able to talk about electrons that are kicked out. It also means that if the photon doesn't have enough energy, the electron doesn't get kicked out at all. There is some threshold amount defined by the work function. And the work function is going to depend on what kind of material you have, which sorts of electrons you're kicking out, if it's one of the outer electrons or the inner electrons, as you might have learned about in chemistry. But this is the basic idea then. Each photon will have a certain amount of energy, and as you see, it does not depend on the amplitude. Instead, we now have to define amplitude in a different way, and basically the amplitude is going to be talking about the number of these photons, basically the energy density in the light. So a really bright light means it has a whole bunch of photons, but each of those photons may have a lot or not so much energy in them, again, depending on its frequency.